Good morning, students. Today I am going to again. I will explain again what I wrote. Now listen it here. We are discussing the line spectrum of hydrogen atom. The line spectrum of hydrogen atom. Before going to discuss about the line spectrum, actually I am going to first write the energy of electron in nth orbit of certain atom. This we derived in the last class. That is equal to minus 13.6 z square by n square. That is equal to if in case of hydrogen atom z is equal to 1, we have to write minus 13.6 by n square electron volt we write. Next, wavelength of emitted radiation also we previously derived in the last class. 1 by lambda is equal to r into 1 by nf square minus 1 by ni square. Where ni is the initial energy state. Okay, ni is the initial energy state. This is the initial energy state. And nf is the final energy state. Then electron starts from initial energy state and it goes to the final energy state, like this transition is occurred. During this some energy releases, right? Electron transition occurred from Ni to Nf. During this it emits the radiation with certain wavelength. That wavelength we can find out by using a formula, that is 1 by lambda is equal to r into 1 by nf square minus 1 by ni square, where r is a Rydberg constant. Its value is 1.09 into 10 to the power of 7 meter inverse. If you find out the 1 by r value, you will get 1 by 1.097 to the power of 7, and this 1 by 1.097 value is 0.9116. In this 10 power 7 goes to numerator 10 power minus 7 meter. This meter converted into angstroms by multiplying with 10 power 10, you will get 912 angstroms. You have to remember the r value and 1 by r value. These formulas are useful while solving the problems. Okay, is it clear, students? Now is it visible, students? Voice and writing clear na? Shushmita Priya Mato. Right. Now I am going to draw one diagram. That is the line spectrum of hydrogen atom. That is the line spectrum of hydrogen atom is that we have to take some lines at here. This spectrum is the group of wavelengths. Okay, and now like this we have to take some lines. This we can consider as the first energy state. This is the second energy state. Okay, second orbit. This is the third orbit. This is the fourth orbit. This is the fifth orbit. Okay, and this is the sixth orbit, and this is the seventh orbit, and this we can, after seventh we will take it as infinite. This we can take as infinite energy state. It is the final energy state. Okay, now this second energy state, this first energy state is said to be ground state. Ground state. If electron excites from here, it will goes to the second energy state, second orbit. It is called as the first excited state. First excited state we can call first excited state. This is n is equal to 3 is the third orbit. It is said to be second excited state. Second excited state. Okay, this has the energy E1. Let us consider its energy is minus 13.6 electron volts. Why? How you got this? N is equal to 1, you substitute in the equation. This way you can consider as equation 1, and this we can consider as equation 2. You see, from equation 1 you write N is equal to 1 for ground state energy. It means 13.6 electron volts. All the electrons which are in the first orbit has the minus 13.6 electron volts energy. In the second orbit you substitute here n is equal to 2 in the equation 1, you will get minus 13.6 by 4, that you will get is minus 3.4 electron volts. And the next one is the minus 1.5 51 electron volts. The next one is the minus 0.85 electron volts. The next one is the minus 0.54 electron volts. And the next one is the minus 0.38 electron volts. Next one is the minus 0.28 electron volts. This is the infinite. N is equal to infinite. You substitute here in the equation 1. Okay. Particular orbit energy we can find out by using equation 1. That is equal to minus 13.6 by n square electron volts. In that n is equal to infinite, you write last orbit. That is n is the orbit number at here. Okay. Orbit number or energy state. It is energy state. Okay. Right. Principal quantum number. This last one n is equal to infinite, you substitute here n is equal to infinite. N is equal to infinite means energy you will get as 0 like this. And now electron maybe transition occurs from where to where. Electron transition maybe occurs from infinite to first orbit, right? Electron transition maybe occurs from infinite to first orbit or seventh to first orbit or sixth to first orbit or fifth to first orbit, fourth to first orbit, and third to first orbit. Transition is going to from second orbit to first orbit next. These are the possible chances to get transition to the ground state first orbit from higher orbits, right? Transition of electron occurred from second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit, fifth orbit to first orbit, third, sixth to first orbit, infinite to first orbit. These are the possibilities. In this case, that is some energy releases, and that energy releases forms a spectrum. Spectrum is nothing but it is a either bright lines on the dark background or dark lines on the bright background. Due to the emission of energy, that spectrum will be forms, and spectrum is the fingerprint to find out certain gas, right? And this will come under the Lyman series. You remember, this is the Lyman series. If the transition occurs to the first energy state from higher energy states from outer orbits, electron transition occurs to the first orbit, right? Is it clear, students? Right. That is the Lyman series. If transition is occurred to the second orbit, for example, transition occurs to second orbit, from where it will occurs from outer orbits. Outer orbits means what? Transition occurs to second from either third or fourth or fifth or sixth, like that, right? For example, if transition occurs from infinite to second orbit or seventh orbit to second orbit or sixth to second orbit, right? Fifth to second orbit, like this. Fourth to second orbit, right? Third to second orbit, like this transition is occurred, and this will come under the Balmer series, right? Balmer series. This Balmer series transition should occurs to the second orbit from outer orbits. If transition occurs from outer orbits to the second orbits, then the energy releases in the form of energy released forms a spectrum. That spectrum series are under the Balmer series, right? This is for the Balmer. Next one is the if transition occurs to the third orbit, right? Like this. Very important topic. I think you know for you are perfect in this topic because it is also available in the chemistry, right? And it is a famous topic in the chemistry. Lyman Balmer, it will come under the Paschen series. Transition occurs to the third orbit. If transition occurs to the fourth orbit, like this. from higher orbits. This will come under the bracket series. Bracket series means transition occurs to the fourth orbit. Right? This is the bracket series. Now, if transition occurs to the next one, transition occurs to the fifth energy state. Okay, transition occurs to the fifth energy state, and then this will come like this from higher orbits. Infinite to fifth, seventh to fifth, or sixth to fifth. This is called as Pfund series, right? And this Lyman series in this energy releases, that energy released in the region, that is in the region of UV. This is in UV region, and this energy released in the region of visible in the Balmer series. Okay, visible region, and then this is in the region of near IR, near IR, and this one is the middle IR. The last one is the last spectral series is the Pfund one, and this is the far IR. IR means infrared radiation, right? That means in this transition in the Pfund series, in the Pfund series, the transition occurs in this energy releases in IR radiation. In bracket also IR, right? In the Balmer also IR, right? But last three series, Balmer, Paschen, bracket are the belongs to IR radiation, and the first one is the UV radiation, and second one is the visible. Okay, we will continue. You take the screenshot. If you have doubt, you must ask me because the clarity is very important. Now let us see here. We will discuss the types of hydrogen spectrum. How many spectral series are there? Line spectrum. That is hydrogen emission spectrum consists of five series. Hydrogen emission spectrum. Emission spectrum has five series. Okay, five spectral series. Then first one is the Lyman series. Second one is the Balmer series. Third one is the Paschen series. Fourth one is the bracket, and the last one is the Pfund series, right? Now let us start. We will discuss about each and everything. First one, Lyman series. Students, is it clear? Lyman series. First one is the Lyman series. The Lyman series in the transition occurs to which orbit? Tell me. Okay, when electron jumps from where to where? When electron jumps from outer orbit to the outer orbit. Outer orbit means what? Higher orbits. Higher orbits are what? 2, 3, 4 like this. Okay. When electron jumps from outer orbits to the first orbit. Outer orbits to the first orbit. Okay. Spectral these Lyman series series spectral lines will be emitted. In this, these are in the When electron jumps from outer orbit to the first orbit, spectral series are belongs to Lyman series, and these spectral lines in this case, spectral lines are in UV region. That means UV rays are emitted during this transition. Okay, what should have? What is the condition at here? Electron transition must occur from where to where, initial energy state to final energy state. During this initial energy state is what? Okay, electron transition occurs from where to where? Electron transition occurs from Ni to Nf, right? Ni to Nf, where Ni is the initial energy state, Nf is the final energy state, right? Then electron transition is occurs from initial energy state to final energy state, Ni to Nf. Then here, what is the value of Ni? Is it fixed value of Ni or Nf? Transition should be occurs finally to the first orbit. Is it right? In case of Lyman series, first orbit, Nf is the one. What is the value of Ni? Transition occurs to the finally one first orbit. Transition should occur to the first orbit. But initial maybe kya? What should be initial? 2, 3, 4. Higher, from higher orbits transition occurs. That's why we write here 2, 3, 4, and so on we can write. In this case, you know wavelength of emitted radiation. To find out that, there is a one formula is there. R into 1 by, what is that? Nf square minus 1 by Ni square. Its formula we derived in the last class, right? And this formula, how it will be changes in this? Nf value is fixed. We write here Nf value is 1. Finally, electron jumps to the first orbit. From where? From higher orbits. What are the higher orbits from than the first orbit? Second, third, fourth are the higher orbits. From there, transition occurs to the first orbit. Second to first, or third to first, fourth to first. Is it right? Okay, are you getting? 1 by 1 square minus 1 by Ni square. First value is a fix. Is it right? This is the formula that we will use to find out the uh, wavelength of emitted radiation in the Lyman series. Okay, for example, if transition occurs from, if transition chances is what? Finally, it should occur to the first orbit. If transition occurs from second orbit to first orbit, what happens? Second orbit to first orbit. Okay, generally, it should occur from Ni to Nf. Okay, for example, transition occurs from second to first orbit. Then what happens? What happens to the emitted energy and emitted frequency and emitted wavelength? What happens? Here in this case, emitted energy, and frequency, emitted radiation, during transition radiation will be emits, energy will emits. That emitted energy and frequency is minimum in this case. Okay, energy minimum and frequency is also minimum. Okay, but the wavelength of emitted radiation is maximum. Okay, but wavelength of radiation is maximum. Wavelength is maximum. Okay, this is the case. Okay, are you getting the points, students? Yes, Bhumika clear. Priyamata asked some doubts. Is there any condition when the electron will come in Lyman or Balmer or series? That is, it may be possibility. We cannot say that how it will be, how transition is occurs. Okay, now I am going to continue, and you request your friends to come to the class. Okay, is it clear till now? And if you have any doubts in the writing and you ask me, you take the screenshot. I am going to take another slide like this. I'm going to rotate it. Now Why, if transition is occurs from second to first, energy released is maximum. I said why it is maximum. Why it is maximum? Okay, see here. What I said that the energy released will be maximum. Okay, when transition occurs from 2 to 1, what I said here, energy released is maximum. Okay, so energy release is maximum or minimum? Minimum. I said energy released is minimum, and the frequency is minimum, right? Energy released minimum, frequency minimum. Therefore, the wavelength will be maximum. Why wavelength will be maximum? Because you know that the nu is equal to c by lambda. Lambda is equal to c by nu. You know, lambda inversely proportional to nu. When nu minimum, automatically wavelength will be maximum. Wavelength will be maximum. Okay, right. In this case, next we will discuss. You see the diagram also. If you want, you see the diagram, and the diagram also gives the clarity for you. That you see the diagram. If transition occurs from second energy state to first energy state, how much energy releases? We will go for the next diagram again. You see this diagram. In this diagram, what we are telling it here? You see here, when electron jumps from second to first, how much energy releases? Energy released, how we can find out it here? Energy released is second orbit energy is minus 3.4, first orbit energy is minus 13.6. Then energy released, what happens it here? E2 minus E1 formula, is it right? Then E2 is what here? Minus 3.4, minus of minus 13.6. Then we will get 10.2 electron volts. Is it right? And this energy, if you energy really, you take the last orbit, infinite energy is zero, right? And if a transition occurs from infinite to first orbit, how much energy releases? Zero minus e2 minus e1. Infinite to first, second to first, we derived the value how much energy releases, that is e2 minus e1 minus 3.4 minus of minus 13.6, 10.2 electron volts energy releases when transition occurs from second to first. If infinite to first occurs, then how much energy releases? Infinite to first means gap is more, the large gap is there, large energy gap, large energy releases. 0 minus of minus 13.6. The final energy is in 0, initial energy is 13.6, then 0 minus of minus 13.6, the energy release is 13.6 electron volts. That means in order to release maximum energy and maximum frequency, when energy is maximum, automatically the frequency is also maximum, because energy proportional to frequency, right? Now what is the conclusion it here? If transition occurs from second to first, if transition occurs from second to first, large minimum energy releases, that is 10.2 electron volts. Okay, if transition occurs from infinite to first, then maximum energy releases. Okay, and let us continue. Right, let us see here. When 2 to 1 transition occurs, energy released is minimum, frequency minimum, because energy released and frequency are proportional. And next, when the energy will be maximum. Okay, and if transition is occurs from next case, if transition occurs from last case is what? If transition occurs from transition, if transition occurs from infinite to first orbit, infinite to first orbit, then what happens? then emitted energy and frequency maximum. Emitted energy and frequency becomes maximum, and but the wavelength is minimum. But the wavelength is minimum. Okay, infinite to one transition. In this infinite to one transition, energy released is okay. Energy released in this case, energy released how much? E2 minus E1. Right, that is 10.2 electron volts. But in this, how much energy releases? E2 minus E1. That is 13.6 electron volts. 0 minus of 13.6. Then this will become maximum. When energy release is maximum, automatically frequency maximum. Frequency maximum means automatically wavelength minimum, because wavelength is inversely proportional to frequency. And the next, this is transition is called as a series limit transition. The above transition, okay, that is from infinite to 1, is called as series limit transition. Series limit transition. Series limit transition in Lyman, right? In Lyman series, it is a series limit. Series limit, why we are telling? Infinite to 1 it is coming. It infinite is a limit. That's why it is called the series limit. Okay. Now, one note I am going to give that if transition occurs from second to first, okay, second to first in the Lyman series, then that is called as first member of Lyman series. First member of Lyman series. Okay, first member of Lyman series. If transition maybe occurs from second to first or third to first, finally it should occurs to the first in the Lyman series. If occurs it is third to first, then it is called as a second member of Lyman series. Second member of Lyman series. If transition occurs from fourth to first, that is called as the third member of Lyman series. Third member of Lyman series, right? Okay. Now this is about the Lyman series. Okay, but the next let us go for the second one. The second one is the Balmer series. In Balmer series, the transition should occur to the first orbit. Is it right? In the Balmer series, transition should occur to the first orbit. Then from where it sorry. Transition occurs to the second orbit from outer orbits. Okay. Then when here the condition is that electron should jump from outer orbits, higher orbits to second orbit. When electron jumps from outer orbits to outer orbits to the second orbit. Okay, then the spectral lines, in this case what happens? The spectral lines are emitted at here. That spectral lines are in the visible region. They are in the visible region. Here transition occurs to the what? Transition occurs to the second orbit. That means finally it should occur to the second orbit. From where it will comes? From higher orbits. Higher orbits means more than 2. Then that will be 3, 4, 5 and so on, right? And up to infinite. Then what is the wavelength of emitted radiation? We write the formula, that is 1 by lambda is equal to R into, we write as 1 by n f square minus 1 by ni square. This formula we know for the to find out the wavelength of emitted radiation, and from this 1 by lambda is equal, we write as R into 1 by NF. Final energy state would be 2, and 2 here NF is 2, we write here 2. 2 square is the 4, that is a 1 by Ni square we can write. Okay, right. Ni may be changes, right? Third to second, fourth to second, fifth to second transition occurs, that all will under the Balmer series. Okay, and now in this, in order to get the maximum energy and minimum energy in the Balmer series, what should be the condition? Can anyone tell? You take the screenshot. In order to release, in order to release maximum energy in the Balmer series, what should be the condition? Can anyone tell? From where to where the transition should occur? From where to where the transition should occur? Right? You, it was very simple. You write in the chart box. In order to get the maximum energy release. Sir, this series for only hydrogen atom. Yes, it is for only hydrogen atom. This I am explaining for only hydrogen atom. Aditi. Next, let us see here. And if transition occurs when electron jumps from outer orbit to the what's happening in the, it is transition is occurs to the second orbit from higher orbits. For example, if transition is occurs from third orbit to first orbit, okay, initial energy is third and final energy is second. That means the transition is occurs from third to second. If transition is occurs to from third to second means gap is less. Gap is less means energy release is less. Okay, energy release is less. Energy release less means frequency less. Frequency less means wavelength will be more, right? Okay, and the next, if transition is occurs from infinite to, okay, if initially infinite and transition is occurs to the finally to the second orbit too. Why we are taking the finally second? In the Balmer finally it should occurs to the second orbit, right? Okay, that means here the transition is occurs from third, sorry, infinite to second. Infinite to second. If transition is occurs from infinite to second, then what happens? If transition is occurs from infinite to second, it is a gap is more. Infinite energy state is at the long distance. Energy released is maximum. Energy released is maximum. What happened? Energy released. Energy released is maximum. Okay, maximum energy releases, and the frequency is maximum, and the wavelength will be minimum. Okay, right. This is about uh, Balmer series. In Balmer series, if the transition occurs from third to second orbit, okay, in the note you write. In exam, no need to write the note pointed here. The note is that if the transition occurs from third to second, that is called as the first member of. In the note here, you write it in the note. In the note, if transition occurs from third to second, finally it should occur to the second orbit in the Balmer series. This is the first member of Balmer series. Third to second. In the Balmer series, transition should occur to the second orbit. Finally, the electron jumps to the second orbit. From where? From outer orbits. From third to second, if it jumps, it is called as the first member of Balmer series. First member of Balmer. Okay. If transition occurs to the fourth to second, right? It is called as the second member of Balmer series. If transition occurs from fifth to second. Finally, it should occur to the second in the Balmer series. This is called as the third member of Balmer series. In exam, they may ask to derive the wavelength of third member of Balmer series like that. Then in that moment, you have to take the value of Ni and Nf from this, right? Okay, this is about the second one. And let us discuss about the third one. Third one is what? What is the name of the third series? Paschen, right? Paschen series. Okay, Paschen spectral series. In this, what happens? Transition from where to where it should occur. If when electron jumps from when electron jumps from outer orbits to outer orbits to the outer orbits to the third orbit. If electron jumps to the first orbit, that are in Lyman. When electron jumps to the second orbit, that are Balmer. When electron jumps to the third orbit, from outer orbit to third orbit, right? Then that are comes under the Paschen series. The spectral lines and spectral series that are in the region previously we said that are in the visible region, right? Oh, what I said, Balmer series, they are in which region? Balmer series in the visible region. Then here Paschen series, the third spectral lines. The spectral lines are in near IR region, near infrared region. Okay, this is about Paschen series. In this, finally the electron should jump to where? It should jump to the third orbit. From where it will jumps? Initial energy state is what? From higher orbits. More than third, higher are what? 4, 5, 6, and so on, right? And then if you want to find out the wavelength of emitted radiation, you have to use the formula 1 by lambda is equal to 1 by r into 1 by nf square minus 1 by ni square. It is the formula to find out the wavelength of emitted radiation. But here we have to take nf is the fixed value. In the Paschen series it is the 3, right? That means 1 by 3 square we have to write nf value. 3 square is 9. 1 by 9 minus 1 by ni square we have to write here. Okay, we are getting here what, right? Now if here in this case transition maybe occurs from, if transition occurs from, transition should occur to the third orbit. From where? If transition is occurs from fourth to third orbit, initially fourth and finally third. That means transition is occurs from fourth to third. If transition occurs from fourth to third, what happens? The energy and frequency will become maximum. Energy released and frequency become maximum. E comma energy released delta E comma nu become maximum and the wavelength will become min. Oh, wrong. Gap is less means energy release is minimum. Why energy release is minimum? Third, fourth gap is less. That means automatically the energy release is minimum. Energy release is minimum and energy release is minimum means wavelength will be maximum. Wavelength will be maximum. And if transition occurs from infinite to third, finally it should occur to the third na in the Paschen series, right? Initially it is at infinite. Transition occurs from infinite to where? Third orbit, right? That is infinite to third orbit means gap is more between the energy states. Then the large energy releases, large frequency releases, radiation releases with large frequency, and the frequency is maximum and the wavelength will be minimum, right? If transition occurs to third orbit at here, fourth to third it will comes, fourth to third, that is called as the first member of Paschen series. Fifth to third, second member of Paschen series. Sixth to third, that is the third member of Paschen series. I am not going to write the notes for that, right? In the note I wrote for the Lyman and Balmer. Similarly it will be there for others. And the next fourth one is the bracket series. What is the bracket series? The bracket series is the when transition occurs from when an electron when an electron jumps from when an electron jumps from outer orbits to the outer orbits to the fourth orbit. Okay, in these spectral lines releases that are in the bracket series, that spectral lines are in the region are in the middle IR region, middle infrared region, middle IR region. In this, what happened? Transition should occur to the fourth orbit. Final energy state is the fourth. From where it will occur? From higher energy states, more than 4 higher are what? 5, 6, 7, and so on, infinite. Right? Now, if transition occurs to fifth to fourth, first member of bracket, sixth to fourth, second member of bracket, infinite to fourth, right? And that is the final last series limit. It is infinite to fourth. It is the series. It is called as a series limit. Series limit. Okay, right. In this, if you write the value of 1 by lambda, okay, and we will continue in the next. You take the screenshot. It was very easy topic actually. uh, because of writing it is taking much time, but it is not that much a hard topic to explain. Actually, I am thinking, is it true, students? It's not hard topic. Okay, let us start. We are discussing the fourth one, right? We are discussing the fourth one. What is this? Okay, let us see here. That is, in this, NF is the 4, right? And the wavelength of implantation, if you want to find out, you have to use this formula. 1 by lambda is equal to R into 1 by NF square minus 1 by NI square. What should be the NF value in this case? In this case, 1 by lambda is equal to R into 1 by NF. NF should be 4. 1 by 4 square. Okay. 1 by 4 square means 1 by 16 minus 1 by Ni square you have to use. Right here, if transition occurs from Ni, that is the firstly fourth, finally it should occur to the fourth energy state. NF should be 4, Ni 5, and NF is 4. Then in this case, what happens? And if transition occurs from fifth to fourth, energy released gamma frequency is minimum and wavelength will be maximum. That is in the bracket series. And if transition occurs from infinite to infinite to fourth, then this is the series limit. It is the last chance is infinite to 4, right? Then the energy released is maximum and the frequency is the maximum and the wavelength is the minimum. These are useful to solve the problems actually, these conditions. Okay, next one is the fifth one. What is the fifth one? What is the name of that one? Pfund series, right? Pfund series. In this, what happens? Transition occurs to the where? Transition should occur to the fifth energy state. Okay, when electron jumps from where to where? When jumps from electron jumps from outer orbits to the fifth orbit. The spectral lines are in the region are in the far IR region, right? In this transition occurs to the where? In this transition occurs to the fifth energy state from outer orbits. Initial energy states are more than 5. That may be 6, 7, 8, and so on, right? And so on infinite. If transition occurs to 6 to 5, that is called as the first member of Pfund. 7 to 5, second member of Pfund series. 8 to 5, third member of Pfund series. Infinite to 5, series limit in the Pfund series, right? Their names you should remember. Okay, and in this case, if you want to find out the wavelength, then we have to use this formula. 1 by lambda is equal to 1 by r into 1 by nf square minus, sorry, 1 by lambda is equal to r into 1 by nf square minus 1 by ni square. In this we have to write 1 by lambda is equal to r into 1 by nf square, that is a 5 square, minus 1 by ni square. It is a easy topic actually, but it is taking the time. In this, what happens if transition occurs from, where sixth to fifth, final energy state is 5, then in this case the energy released and the frequency will become minimum and the wavelength will become maximum. If transition occurs from infinite to fifth orbit, right, and in this case energy released comma frequency will become maximum and the wavelength will become minimum. This is called as a series limit. In the series limit, this is series limit in what, in which series? Pfund series, right? Okay, this is about spectral line spectrum of hydrogen atom. Is it clear, students, till now? Huh? Okay. Next, we will discuss one important topic. That is, what are the limitations of Bohr theory? Okay, limitations of Bohr theory. Very important. What are the limitations? It does not explain something, right? Bohr model, and every model has some limitations. Rutherford J. J. Thomson model we discussed, Rutherford model we discussed, Bohr atomic model we discussed. Our chapter name is atoms. We are discussing about the atom and particles which are there in this and atom properties, right? And limitations of Bohr's theory, right? What are the limitations? I these things also in previous classes. Okay, in the chemistry. Just I will give the notes. Okay, it could not explain the spectra of it could not explain the spectra of complex atoms complex atoms having more than one electron. What is this? It does not explain the spectral series of Bohr theory. Does not explain the spectral series of complex atoms having more than one electron. Means this is applicable for only Bohr theory is explains for only hydrogen atom, right? Explains for only hydrogen atom. Other atoms, helium, neon, more than one electrons, if they have, that is not explained. Bohr theory explains only applicable for only hydrogen atom. Okay, explains for only hydrogen atom. This is the first point. And hydrogen atom only have the one electron. Na? More than one electrons are there means that is not explaining. Bohr theory is not explained. Okay. And the second one is that it could not explain binding energy of atoms in molecules. Binding energy of atoms in molecules. Okay. how molecules atoms are bound in the molecule, that not explained. Okay, next points. Next point, limitations I am explaining actually, and the limitations we will see here. Third point I am going to explain. Okay, third point is that it does not give any idea about the relative intensity of spectral lines. Next, fourth point is that it could not it could not account for the wave nature of electron. Wave nature of electron also not explained. Next, fifth point, last point. Bohr model involves electric force. Bohr model involves electric force between nucleus and electron. Does not include the electric force between electrons. Okay, Bohr model is explained by considering the attraction force between nucleus and electron only. Nucleus is positive charge and electron is negative charge, but not included the force between the electrons. Okay, these are the some limitations. And the next topic is very very important for the 3 marks. Many times it came in the board exam, and either it will be based on that you may get problem or you may get theory as it is. That is the De Broglie explanation of De Broglie explanation. De Broglie explanation of De Broglie explanation of Bohr's second postulate. Do you know what is the Bohr's second postulate? Anyone can type in the chat box what is the Bohr's second postulate. Bohr gave only three postulates. Then what is the Bohr's second postulate and how Bohr's second postulate is explained by de Broglie? Can anyone tell what is the Bohr's second postulate? Write in the chat box. Do it fast. Bohr's second postulate. What is that? Okay. For that, let us see here. This is a orbit. We will take this as one orbit. Okay. And this is the one nucleus. This is the nucleus. nucleus charge is plus Ze. It is the nucleus charge is plus Ze, and the radius we can consider as r. Here this is an electron, and this electron is moving with some speed at here. The electron mass is m, and when electron moves at here, according to de Broglie, every moving particle is associated with a wave. Is it right? According to de Broglie proved the Bohr's second postulate. Can anyone type what is the Bohr's second postulate? Do it fast. Aditi, Priyamato, Twinkle, Sushmita, Sunita, Ratika. What are you doing? Do it fast. Right, Priyamato. MVR is equal to NH by 2. 2 pi. Good. According to Bohr's, sorry. According to de Broglie proved the Bohr second postulate, right? And according to de Broglie, what is that? We discussed the de Broglie hypothesis in the dual nature of radiation and matter. What is the de Broglie hypothesis? According to de Broglie, right? Every moving particle, every moving particle is associated every moving particle is associated with a wave. This wave is called as what? This wave is called as, you know that one already. This wave is called as a matter wave. Can anyone tell the formula for the de Broglie wavelength? Matter wave wavelength. For example, m mass of particle moving with velocity v. According to de Broglie, a wave is associated with that. A particle is moving means wave is moving. He linked the wavelength, he gave the wavelength of the moving particle also. Particle gives like wave, he said. Then what is the formula for the wavelength according to him? Right? Can anyone type? According to de Broglie, write in chat box. According to de Broglie, standing waves, standing wave is produced in orbit. Standing wave produced in orbit with circumference is equal to the n lambda. What de Broglie said? Anybody wrote? What is the de Broglie wavelength formula? De Broglie wavelength formula from dual nature. And here de Broglie explained this moving particle. One electron is moving in the orbit. One electron is moving in the orbit. That moving electron also associated with some wave. Moving electron also associated with some wave. That wave he gave here. And this wave is the standing wave, he said. Standing wave means what? Stationary wave. Okay, that is produced in the orbit. When electron moves in the orbit like this, in the figure you see, then one wave is associated with that electron. That wave is the standing wave, stationary wave like this. When electron is moving, then we say that the wave is moving. Like this, one wave is associated. And then that circumference of the orbit, circumference means 2 pi r, right? Circumference is the 2 pi r. He said the circumference of orbit, that is 2 pi r, is equal to n lambda. So n lambda. Why? Because for example, this is the one wave. One wavelength is what? Lambda. Like this, for example, n waves are formed. This is one wave, one crest, one trough. Like this, if n waves are formed in the orbit, then we write its length is equal to n lambda, circle length is equal to pi r. He said like that. Okay, I'm going to continue to take the screenshot. Let us continue it here. You see this picture. What we're telling it here, for example, in this wave, okay, electron is moving in the orbit. Electron is moving in the orbit, and then with that one wave is associated, that is a stationary wave. This wavelength is the lambda. Like this, if n waves are formed, then the full circle length will become n lambda. Then according to the de Broglie, we can write it as 2 pi r is equal to what he said, 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. Okay, and then here, but we know one thing, where lambda is the wavelength, lambda is the wavelength, r is the radius of orbit, radius of orbit. But we know according to de Broglie, but de Broglie wavelength formula is what? Anyone write in the chat box? Yes, Twinkle wrote that 2 pi r equal to n lambda. Very good. And this is from the de Broglie hypothesis. But in terms of wavelength formula, okay, de Broglie wavelength formula previously they gave, right? And de Broglie wavelength associated with the electron which is moving along the orbit. De Broglie wavelength associated with electron is what? That wavelength we can write as, you know that formula, this we can consider as equation 1. And what is the wavelength? M mass of particle moving with speed v, and the wavelength associated with formula is h by mv. This we can take as equation 2. Now what you have to do it here, equation 2 is substituted in equation 1. I am asking the equation 2 actually. This is the formula for the wavelength associated with electron. Okay, equation 2 substituted in equation 1. If you substitute in equation 1, then what you will get? 2 pi r is equal to n lambda, where lambda is h by mv. Is that right? Then here what you will get? We take this mv to left side, 2 pi to right side. mvr is equal to, we will get as nh by 2 pi, right? Okay, what is mvr? What is m? Okay, this is only angular momentum of electron. Is it right? M is what? Mass of electron. And v is the speed of electron in orbit. And r is the radius of orbit. N is the principal quantum number, orbit number. Then the proof is completed. Is it right? From the above, this angular momentum of electron, mvr is angular momentum of electron, equal to integral multiple of h by 2 pi. Okay, then this is the Bohr second partlet. Therefore, Bohr's second postulate derived, right? Is it right? Proved from de Broglie hypothesis. Have you understood, students? Is it clear, students? Aditi, lambda equal to h by mv, right? Is it clear till now? This is most important. Whatever that you are seeing in the on the board, okay, and that is very important for the 3 marks. It is a previous question. Many times it is repeated in the exam. They ask to derive the Bohr second postulate from the de Broglie hypothesis. Okay, right. The next, let us go for next point. Some points I am going to explain. Is it clear, students? You write in the chat box. If you have any problem, you write in the chat box. Let us continue now. Some important points in the note I am going to give. The important points are the first point is that when an electron jumps from when an electron jumps from n2 energy state to n2 energy state to n1 energy state, n1 energy state, then the number of spectral lines, then the number of spectral lines, then the number of spectral lines emitted. I want what happening at here, electron jumps from n2 to n1, electron jumps from n2 to n1, then how many spectral lines releases, then the number of spectral lines formula is there. There is number of spectral lines formula is there. There is a shortcut like, okay, that formula is n2 minus n1 into n2 minus n1 plus 1 by 2. This is the formula. What is this actually? What is the use of this one? Okay, this is just like this. We can also write one more important point set here. Actually, this is for example the third energy state. Okay, n2 is the third energy state. And for example, electron is jumps to n1. N1 is considered as the first energy state. Then how many possibilities are there? This is the second energy state. How many electrons releases? For example, when electron jumps from third to first, electron jumps, transition occurs from third to first, n to n1. Then how many spectral lines can emitted? How many spectral lines emitted? For example, third to first, n to n1 directly it will comes. Okay, one spectral line is emitted. Or third to second it will comes. Next second to first it will comes. At 1, 2, 3 spectral lines came. Okay, like this there are some possibilities are there. For example, n to 3, n1 you write 1, third to first, 3 minus 1, 2, right? 3 minus 1. If electron transition occurs from third to first, then how many spectral lines can emit? Third to first directly comes, third to second, then second to first comes. Then how many lines are emitting it here? 3 spectral lines are emitting in this. Whether by using this formula we will get the same or not, we will see. 3 minus 1 into 3 minus 1 plus 1 by 2. It is the formula. N2 is 3, N1 is 1. Okay. Then we are getting the 2 into 2 plus 1, 3 by 2. Then how many you are getting? 3 spectral lines. You see 1, 2, 3 like this. This is a very small one. We find out it here. This is the one. This is 2 and this is 3, right? 3 lines are embedded here. For example, if complex, if 10 to 1 it is released, 10 to 1, then it is very difficult to find the number of spectral lines. That's why we use uh, this formula. It was very easy to find out the number of spectral lines. Number of spectral lines, it is in the note. Okay, in the are you understanding? That's one more point. If electron jumps from n2 is n, let us consider n2 orbit to n2 is nth orbit to first orbit. Okay, n1 is 1. That is the ground state. Okay, transition is occurs from nth orbit to first orbit. Transition occurs from nth orbit to first orbit. Then how many spectral lines will releases? Number of spectral lines formula, what happens? N2 first it will come. Then here write N2 is N, N1 is 1, N minus 1 we will get here, and here N2 is N, right? N1 is minus 1 plus 1, it will become N. Then we will get like this, N into N minus 1 by 2. This is the number of spectral lines releases when transition occurs from nth orbit to ground state, first orbit. Okay. Next, if delta is the delta E is the energy difference between two energy levels. Okay, then wavelength of emitted radiation during transition of electron between two energy states. What I am telling it here, you get here, and this is the one energy state, its energy is E2. This is energy, other energy state. Energy state means orbit only. This is, for example, some orbit. All the electrons in the subparticular orbit have the same energy. Now what happening it here, electron jumps from higher energy state to lower energy state. When electron jumps from E2 to E1, then energy releases. Is it right? What releases? Energy releases. That energy releases is the delta E. Is it right? It is the energy, it is equal to what? You know that one? Delta E is equal to difference in the energies of two energy levels. You know that one, right? Energy levels, difference in energy levels. I want the wavelength of emitted radiation during this transition. How much wavelength will emit? Lambda is equal to, if you want to find out. It was very easy to find out according to Bohr's third postulate. Energy released is equal to E2 minus E1. That will releases in the form of photon. Is it right? We write like this. Delta E is equal to h nu. H nu we write as C by lambda. Then from this we write, if you want to find out the lambda, okay, we can find out that is very easily. That is hc by delta E we write. Hc by delta E we write. Okay, this is in the note, and we will go for some more points. We will discuss about some more points. So, okay, actually, more 5 minutes required to complete this chapter, and but we have to discuss the problems. Okay, the problems are very important in this chapter, and I am thinking to close this topic within 5 minutes, and after that, in the evening, I will start. In the night, I will take again the live class, and in that, I will explain the problem. Will you come to the live class in the night time? Priyamato, sir, number of spectral lines release. Okay, I will explain the problem at the moment you will understood everything. Okay, don't worry. Huh? In the evening, I will explain the problem. Are you ready to come to class in the evening? You write in the chat box. In the night time, I will take, not in evening. Night time, maybe in the night if possibility is there. Okay, and I will close the topic within 5 minutes. Very less members are there. Only 7 members are watching in the live. Very dangerous it is. Huh? I'm giving the much time for you, but you are doing like this. Very disappointing me. Okay, right. I am going to continue. Okay, next 5 minutes I will close the atomic spectra. Next topic. What is atomic spectra? Atomic spectra is that when electron jumps from when atomic spectra, you know that one. When an atomic gas, some gas is there, is excited. Gas is excited by passing current current through it. When atomic gas is excited by passing current through it, the emitted radiation has spectrum. Spectrum means only lines, bright lines or the dark lines. Okay, bright lines on the dark background or the dark lines on the bright background. Emitted radiation has a spectrum called as emission spectrum. When emission spectrum will occurs, the emission spectrum has bright lines, on a dark background. Okay, emission spectrum, how it will be releases? Just for example, you can, this is a gas. Okay, this, it has some atoms. You can pass some current. Okay, and make the all the electrons to excite. All the excited electrons will go to higher energy state, and they will return back here. Now again, all the excited electrons will come back to the ground state, and during that energy releases, the energy releases forms the bright lines in the dark background. That spectrum is called as the emission spectrum. How emission spectrum will forms? Because of transition of electron from higher energy state to lower energy state. When electron transition occurs from higher energy state to lower energy state, then energy releases, that energy released forms the bright lines on the dark background. Okay, here one energy releases. Emission spectrum has the bright lines on the dark background. Next, let us go for one more point. That is absorption spectrum is what? What is absorption spectrum? Absorption spectrum means what is the use of this spectra actually? Okay, before going to that absorption spectra, we will write when an electron when an electron jumps from, sorry, If I will use absorption spectrum, can anyone have the idea for the absorption spectrum? Write in chat box, please. Oh, from 1.5 hour onwards, we are discussing. That's well, even my pen tab also not working. When electron jumps,